Thank you for the introduction. So today I would like to explain the proof of this theorem in SGA2 I stated yesterday. So the theorem is the following one. So X smooth projective over some field K of pure dimension D. Y is an ample effective divisor in X. I want to prove that when the dimension is at least 2, for any vector bundle E over X, the map from the regular section of E over X to its formal section over the formal completion along Y is an isomorphism. That's the first part, some kind of comparison theorem. On the second part, assert that if the dimension is at least 3, then any vector bundle let's say curly E over this completion is algebrizable. So it means that it is a restriction to the formal completion of some, let's say, vector bundle on some Zariski neighborhood of Y in X. Okay. So maybe before I really discuss the proof of this theorem, of course the proof will use the same kind of trick I explained yesterday that was introduced by Grauert and Spencer, but maybe I would like to give some concrete examples of algebrizable or non-algebrizable, let's say, line bundle on some very concrete algebraic varieties. So an example. Assume you start, well, let us work over a field of characteristics 0. And let us consider M, let's say, a smooth K-scheme. And assume you are given some vector bundle E over M. Okay. In that case, you may consider the total space X of this vector bundle. So in traditional EGA notation, it's denoted V of E dual, because it corresponds to the scheme over M that is affine and which is attached to the quasi-current algebra that is a symmetric algebra of E dual. Spec M of S star E dual. This is a direct sum of the symmetric algebra of symmetric power of E dual. So total space. Of E. Okay. So it's, you see something like that. You have M, and you have family of the fibers. So this is X. Let's call this X. And inside this big X, you have a copy of M. That is a zero section of this. So you have Y equals image. Oh, it corresponds to the sheaf of ideal defined by the augmentation. I of Y. It's very concrete. Okay. And now you may consider the formal completion of X along this Y. So it's something very simple. It's the total space of E over M, but considered only in the informal geometry at the infinitesimal level along the zero section. So formal completion. So it's something very concrete. It's a limit. It's associated to the limit to the system of successive seconding of Y in X. On this Yn is something quite concrete. Yn is spec. It's fibered over M, and it's defined by the coherent algebra. That is the sum of the Sk of E dual for k at most n. So it's an algebra of truncated polynomials. Okay. So of course, when you take divided this by the set of its radical, you get O of Y corresponds to the fact that theoretically all the Y's coincide with Y. Okay, so concretely, you see, if you take Q, something open in Y, and Y is the same thing if you want as this, the sheaf, well, the sheaf of regular function in this formal completion in this U, that's something quite concrete. It's this limit of Y and U. So it's an element of this limit of gamma over U Sk E dual. So this is a kind of completed well, it's a kind of section of the completed so if you can write this by telling that X equals that kind of completed symmetric power of E dual. It's a formal series in the vertical variables. Very concrete thing. Okay. Okay, this is quite elementary. So let me now describe a very simple construction. Of course, here inside, for instance, you may consider gamma U of E dual. So it corresponds to the function, the formal function on the fibers that are linear on the fibers. So in this way, you have a map of sheaves morphism of sheaves of abelian groups. Over Y. Actually, here you arrive in the ideal that defines Y inside. So ideal, let's call it I hat, which is an ideal sheaf there. Okay. And now I claim that you have a morphism of sheaf from here, from this to the unit there, which is again a morphism of sheaf of abelian groups, defined by a formal version of the exponential map, exp. So it's something quite simple. If you have some section here, you may consider this series. And actually, it converges over every U in that kind of algebra of formal series, because it starts with zeros and so on. And actually, you see, actually we will be interested in this the restriction of this map to the linear functions. We will be interested by the composition of the inclusion of ideal in EY, and you have this exponential map. So in that case, it's still, of course, given by this formula. And in this formula, you see it's really a formula where this makes sense in this direct sum. Alpha k over k factorial is something in gamma u sk ideal. This is quite elementary and quite concrete. And what it is really important is that the proof that exponential a plus b equals exponential a times exponential b uses only the formal properties of the exponential map, and it leads to the fact that this morphism is indeed a morphism of sheaves of abelian groups. Okay? So far, so good. So now, assume you are given some class alpha in H1 of M. E. M is the same thing as well. Okay. So you may apply this morphism of sheaf to this cohomology class. So by using this exponential construction, you get a class in H1 of M topologically, but let's write it like this, in the units. So it's quite concrete. The class here is defined by cocycle, alpha ig, finite covering, and a cocycle. And here you consider the exponential of cocycle. So alpha ig is over ug, and this is over the same thing you see as some open set over there. But you have to think of this as some unit in the, let's say, infinitesimal neighborhood of this open UI intersection OJ in this formal total space. Okay. So you see, from any class here, you get a class there. But of course, a class there is exactly an isomorphism class of an invertible sheaf on the formal completion. This is pick. The invertible sheaf that is precisely defined by this cocycle. Okay? And now I claim, okay, this is a very simple construction. Of course, if you work over C, you can do this construction in the analytic setting. You see, you can get a class, an analytic class in the total space without not this formal completion. Okay? And now I claim the following thing. Very easy proposition. So let's denote by L alpha the line bundles defined by this construction from a class alpha. So I claim the following, that the following assertions are equivalent. L alpha is algebrizable. I claim that this holds if, well, if only if F alpha, L alpha is trivial. And that is old precisely when alpha equals 0. So I claim that whenever you start from a non-zero cohomology class, you get a non-algebrizable line bundle by this very simple construction. Okay? And now the proof of this is very simple. The point is that okay, if you restrict L alpha to the 0 section, of course you look at this exponential of 0, and it's a cocycle which is 1. So you get that this is a trivial line bundle. So if this formal line bundle is algebrizable, it is a restriction to the formal completion of a line bundle on your variety X that is fibered with affine fiber over the space M. But you know, recall, okay, if you call pi the projection map, and you have epsilon, the section, that pi on epsilon define isomorphism between these two Picard group. If you have an algebraic line bundle on the smooth variety X, it is defined by a divisor, and now you may multiply this divisor by some any element in K star. You get a divisor, and when you specialize you go to infinity, you get a divisor that is vertical, and that comes from the base. Basic definition of linear equivalence of divisor. So here in this direct direction, it's this, and in the reverse directions, it's pi star. You see an algebraic line bundle on X that is trivial on the 0 section Y or M has to be trivial. So if our L alpha is algebrizable, because of this and that, it has to be trivial. And so it proves the first equivalence. And of course, from the line bundle L alpha, you recover the class alpha simply because, okay, if you look at L alpha restricted to the first infinitesimal neighborhood, so it's an element in the kernel of the Picard group of the first infinitesimal neighborhood to the Picard group of Y. And if you analyze what it is, you see that it is basically defines an element in the unit of O of Y1, which corresponds to that vanish on Y, and this is basically the same thing as H. Define that vertical linear functions on the fiber. So this group may be identified with that. So whenever you are trivial on the first infinitesimal neighborhood, the class alpha has to be 0. And this completes the proof of this equivalence. So you see you have very, very concrete ways to construct a non-algebrizable line bundle. And for instance, you can do that for P1 inside P2, because of course the complement of the point at infinity corresponds to this construction applied to O of 1. And in that way, you get very interesting non-algebrizable analytic line bundles that are non-algebrizable indeed in a much stronger sense than the one I described yesterday by taking a small transversal. You can prove, but it's much more serious work, that they are not defined by an analytic divisor even in a small neighborhood of P1 inside P2. So you see you have, once you, okay, I wanted to give these examples for various reasons, but the first reason is okay, you can get very concrete in this context, quite non-trivial examples of analytic objects that do not algebraize and are rather tricky things. Okay. Okay. Okay, so now let us return to this theorem and to its proof. So let us start by the first assertion. So actually, for instance, in the case where Y is a surface, when X is a surface, when D is 2, exactly 2, and Y is a curve, and Y is smooth, this theorem is closely related to the theorem I proved in the first lectures. Because if you consider a formal section of E, like this, so maybe some comments. D2, Y smooth. If you take a formal section of E, you may consider the graph of this formal section inside the total space of E over X. Think of the analytic situation. You have a formal analytic section. You look at its graph or its image in the total space of the vector bundle. And this will be exactly, okay, this will contain, well, this is some kind of analytic ribbon, like in this first theorem by Andreotti and Grauert. So you know by Andreotti, Grauert, and Andreotti Archard, so he's called this V, that it is algebrizable. So to complete the proof, you will need to know that it's not only algebrizable, but that it is the graph of a regular function. And this can be proved. So exercise. Prove that it is associated, well, it is a germ of the graph of S section of E over X by using Hodge index theorem. So let me explain what you are supposed to do. You look at this graph, you take its closure in some projective completion of this total space, and it will be some surface that will map possibly with a degree larger than 1 to the base. And you want to need that the degree is 1. And this is an easy as a consequence of the Hodge index theorem on this surface. Consider the closure of the graph inside, let's say, some projective completion of this, and show that the morphism from this closure to X, the vertical morphism, has degree 1. Okay. So this theorem is not completely unrelated to the previous theorems, but here actually it's possible to give a very direct proof using a little bit of cohomology. So let me, here in this proof, actually the proof will work with a weaker assumption than okay, for simplicity, well, it's at the same time more general or more restrictive. Maybe I will assume basically X normal will be enough for Grauert 1, and X on Y normal will be enough for Grauert 2. Okay. Okay. So now, actually, it's possible to give a simple cohomological proof. The point is that you have the following short exact sequence of line bundles, well, of a coherent sheaf. So you look at the Cartier divisor n times y, and you have this short exact sequence. So of course, this Cartier divisor is a subscheme, and this subscheme is the same thing as the n minus 1 infinitesimal neighborhood of y. This looks a little bit surprising, but it's true. Well, the indexing in all these things is always a little bit puzzling. But when n is 1, here you get y, and y it is on 0th infinitesimal neighborhood. Okay. This. And now you twist this by E. That is locally free, so you still get a short exact sequence. And you look at the long exact sequence in cohomology associated to that. So you get that. And you see, here you have it. And the point here is that this H1 group vanishes if n is large. Okay, so this is some, of course, today it doesn't look that surprising when you look at, when you study algebraic geometry in Archon's book. It's proved on state as something very basic. It's a so-called Enriquez-Zariski theorem. Actually, it's true that historically, well, Zariski spent a lot of time securing this proof and giving some completely correct argument for some, well, older version due to Enriquez, that is not expressed in terms of H1, but that it's expressed in terms of restriction of linear systems, of complete linear systems. And it took him a lot of work. And quite clearly, one of the great achievements of Serre in faisceux algébrique cohérent had been to use this new sheaf theoretic method to get a much simpler proof of that. And quite clearly, Zariski was extremely impressed by that and made a lot of publicity, organized some summer school on Serre's paper and so on. So from modern point of view, if you learn algebraic geometry in art charts, these vanishing theorems look quite innocent, but historically it's certainly one of the achievements of the new sheaf theoretic methods introduced by Serre in algebraic geometry. Okay, and here is the proof, of course. So, because of course the first, this is clearly, it's very easy to see that this is 0 for n large enough. Exercise, very easy exercise. And from this you see that when n is large enough, this is isomorphic to that, and it is isomorphic to the projective limit. Actually, you see you have a stronger result. Actually, it's, the projective limit defining the section of E on the formal completion. This projective system is eventually constant. At some point, all the things are the same. Okay, let us now turn to Grauert 2. Or maybe I should say, yes, of course, from a modern point of view, you would say, in the smooth case, this is, of course, by duality, by Serre duality, it's the same thing as E. Duo n. The smooth case. And you see, the point is that this D minus 1 is at least 1. So when n is large, by Serre's vanishing, this is 0. That's the point. And behind the proof of Enriquez theory, there is some kind of hidden duality argument that for which the validity of which still holds, let's say on surfaces on in dimension at least 2, with only a normality assumption. That's a way to understand it. Now let's turn to Grauert 2. So the key point, the key is a finiteness lemma, as in the various proof I discussed yesterday. The proof of Kudra and Spencer, on Serre's proof of Gaga, and Grauer's proof of solution of the Levy problem. So we will use finiteness argument on finiteness property on H1, and the same kind of nice tricks using the long exact sequence with 6 terms. So it's a fact that for any vector bundle E over the formal completion. So you can think, as explained yesterday, of a vector bundle over the formal completion as a compatible system of vector bundles on the successive sequenings, Yn's. And then you may consider H1 of this vector bundle. And here, Okay, in this, it's the H1, but in this lecture, you could define it in some slightly ad hoc way as the projective limit of the H1 of the successive seconds. Well, it's true that it's true that if you define the left-hand side as the H1 of this with value in this sheaf, it corresponds to that. But we will not need it. It's a little bit like the fact that when you deal with coherent cohomology of quasi-coherent sheaves, it's true that the cohomology of quasi-coherent sheaves on noetering schemes is their cohomology as sheaves of abelian groups. But in a sense, you may also define it as a Czech cohomology of what it is. And it's enough in real life. And you don't basically very rarely need to know the proof that it coincides with direct definition. Okay? So let's define this as that in this proof. So the key finiteness lemma affirms that this is finite dimensional. Is a finite dimensional K-vector space. Actually, it will be finite dimensional because a much stronger assertion is true, namely that this projective system is eventually constant. So H0, no, H1. Is eventually constant. Okay. Let us prove this. It's very easy, actually, at this point. It's a variant of the previous kind of argument with a 0 and 1 dimensional cohomology. Well, not really. Well, it's very easy anyway. So proof of this lemma. So I may consider the sheaf of functions over yn. A function over yn restricts to a function over the n minus 1 neighborhood. And the same kind of argument as in the previous lecture tells you that the kernel is a sheaf supported scheme theoretically supported on Y, which is the nth power of the dual bundle of the dual of the normal bundle. So n is by definition OX of Y restricted to Y. So n dual is the same thing as the ideal sheaf of Y restricted to Y. You have this short exact sequence. So here again, you tensor it by E. And, well, if you want, you tensor it by E bar. So it corresponds to look at the following things. You get in concrete terms, you get En At every step n, you may consider the section of En, section of on the n's infinitesimal neighborhood. They restrict the maps onto the section of the n minus 1 infinitesimal neighborhood, and you identify the kernel as a vector bundle on Y. That you get twisting E0, E on Y, by the nth power of the conormal bundle. Same kind of thing we did in the first lecture. Okay? And from this short exact sequence, you get a short exact sequence of H1 groups. H1 along Y. Okay. And now look. Here, Y is normal of dimension d minus 1. And in Grauert 2, d is at least 3. So d minus 1 is at least 2. On n, it's a restriction to Y of O of Y. So it's all, again, ample. So here again, when n is large enough, you get that this is 0. By Algébrisation. Okay. So for n large enough, this map is an injection. And of course, here we are dealing with H1 groups of current shift from some projective variety. So these K vector spaces are finite dimensional. So you see, if you look at the dimension of these H1 spaces as a function of n, you get a sequence of integers that, that doesn't increase. So again, it has to be constant when n is large. So constant dimension for n large. So you see that when n is large, it is an isomorphism. And it proves exactly what I have asserted in this lemma. So you see here, in this situation of formal geometry, the finiteness, the key finiteness assertion, that in the context of Gaga or Grauert was a deep analytic thing. Here, it's basically, it's related to some subtle but, let's say, classical finiteness or vanishing theorem, namely the theorem of Henriques-Zariski. But in a sense, formal geometry is formal. You have no deep analytic, well, of course, an argument. So you see, you are always dealing with eventually constant projective systems and so on. So actually, you may make a remark at this point. observation. You could do the same argument not with h1, but with h0. And you see very easily, of course, as n is ample on a curve, on something at dimension at least 1, the section of this has to be 0 when n is large enough. Well, you need to know a little bit of commutative algebra to do that, of course, because you need to know you have no immersed point. But it's true for many reasons.
You are assuming non-singular y, non-singular in dimension 1, because otherwise the normality...
Yes, yes. Here I explain that the proof is okay with y on x and y normal. To be... Of course, it's always true, but it's simpler in this way. I wanted to avoid any kind of allusion to depth results and so on. Okay. The same reasoning. As soon as you are in dimension 2, at least 2, if you consider a formal vector bundle, you get that the space of sections, so defined as this projective limit, is finite dimensional. And actually, this is eventually constant. Same reasoning, but actually simpler, because you don't need a vanishing for h1 and only a vanishing for h0. Okay. Okay. And now, the most we can copy the amount of Grauert and Spencer. So you can copy. So let me recall the kind of argument. The argument was based on a long exact cohomology sequence. So here it will take the following form: h0, xy, e, tensor O of n minus 1y, h0, xy, you have this long exact sequence. H1, you have the same thing. Okay, you have this long exact cohomology sequence. Okay, these groups are defined as projective limits, but it's some kind of trivial projective limits. You may write the analogous short exact sequence with finite rank sequenings, and when the order of the sequenings is large enough, it is that, because all the projective systems defining all these things are eventually constant. Okay, so you get this, and you can play the same game. Remember the game. You say that when n is very large, the last h1 vanishes by its pure algebraic geometry. So it means that this map are surjective when n is very large. So you look at the dimension of this, the dimension decreases. So when n is large, this dimension has to be equal. So this has to be an isomorphism. So this map has to be 0, and this has to be onto. So you get that when n is very large, every section of E twisted by the nth power of the ample line bundle O of Y comes from a global section, but global on the formal completion. But of course, it's clear, well, it's well known, that when n is large, this, if you twist by a very large power of this O of Y over Y, this vector bundle is generated by its global sections. So you see that at the end, this space contains enough sections to generate this vector bundle over Y. But you work in formal geometry. To generate over Y is the same thing as to generate over X over the formal completion. So in this way, you prove so, brief. So the Kodari-Spencer trick based on the finiteness, on the key finiteness, show that lemma for any vector bundle E over X, Y hat for n very large, E is generated by its global sections. Over the formal completion. And now, from this, it's very easy to complete the proof. So by some tricks that are actually already occurs in Gega's proof. So you apply the lemma. You are given some E. You want to algebraize it. So you apply the lemma, and you find a family, finite family. You can find some n, large n, a finite family of sections of E twisted by O of ny. That generated. So it means that you have a short exact sequence like that. Take the sum of a finite number of copies of the trivial line bundle. And this is given by this line vectors. Okay, so this is onto. So at this stage, you may consider the kernel of this morphism. To define this kernel, and it's very easy to see that it is, of course, a current sheaf on the formal completion, and that it is locally free, so because the map is onto. Okay. Bis repetita plaquette, what you have done with E, you can do with F. So you apply the lemma the second time to F. So you can find lemma applied to F. You get some positive M and some finite family T beta. So T beta will be in the section, global section of F twisted by M times Y. And you have this. And of course, now you can glue together these two short exact sequences. This short exact sequence, actually you can, twist everything by the suitable power of O of Y. So from this and that, you get a length 2 resolution of E. Here you have O. But here you have to take minus ny. And here you have, it says, a composition of I on T, which comes from the sum of B copies of O of minus n plus my. Okay? You get this presentation. But look, here you have the morphism, this composition. But this morphism is a morphism between the sum of copies of this line bundles to a sum of copies of this line bundles. So it's given by a matrix of a morphism from this to that. So this is something which is something like a matrix of size M A times B. And the coefficients of the matrix are sections over the formal completion of O of my. And now you are done, because by Grauert, a formal section is the same thing as an actual section. So you can. And you are done. This is you get some morphism from that to that. And you may consider the co-kernel of phi between from this to that, but without completions. And this co-kernel gives you exactly a current shift that algebraize this E. Okay? So that's it. Okay. Okay. If I am allowed to take 2 or 3 minutes, I would like to give a slight development of the example concerning total space of vector bundles. May I? So let me give an application of these results. To some very old results of Franco-Italian geometry. application. Picard-Severy. Theorem on the regularity of adjoint systems. So in modern language, it's known as Kodara vanishing on surfaces. On the following assertion, theorem, let's consider M a smooth projective surface over K of characteristic 0. You take L on ample line bundle on M, on Kodara vanishing assert that H1 of M L dual is 0. So, of course, by the standard way to phrasing Kodara vanishing is H1 of M L times omega M is 0. But these two assertions are equivalent by their duality. Okay? So this theorem is maybe the first of a long series of theorems that led to the kind of result of Ryder that was mentioned in last talk by George. Okay. You can prove this by using the previous construction of algebrisable line bundle from a cohomology class. So you take X as before, V, M, L dual. Now, if L is ample, it's very easy to see that, of course, this is not projective, it's quasi-projective. But when L is ample, it's very easy to see that you can get a projective completion by adding, so to speak, one point at infinity. So, 1 point. Completion. And actually, you see that Y, that is M, embedded by the 0 section, is an ample divisor in that case. So you see, more or less by construction, you see O of Y restricted to Y, the normal bundle of Y in M is exactly the line bundle you started with. The normal bundle of the total space of L, if you look at along its 0 section, is L. That's what I say. So I claim that it's not only ample restricted to L, but it's very easy to see that it is really ample everywhere. Okay? But now look, you can, if you add any class alpha, you may consider its exponential, defined as before. It's an element there. And actually, M is of dimension 2, X is of dimension 3. So you may apply Grauert 2. So it's algebrisable. So alpha vanish. So it's a purely algebraic proof, so to speak, of this Kodara vanishing theorem. So there are a few other ones in the literature. There is one by Mumford, there are at least 2 by Mumford. So in all this proof, of course, you need to use somewhere that the base field is of characteristic 0, simply because there are some nice examples by Michel Reynaud where it doesn't hold in positive characteristic. And here, in this proof, you use it in a very clear and simple way. You use it because to define this exponential map, I really need the fact that we are in characteristic 0 because you have these denominators. And in this way, you get a simple proof. Actually, well, I was very pleased to realize this. You could argue in this way a few years ago. But more recently, I saw that in the literature of the 70s, some people mentioned that Grauert also had some purely algebraic proof in this case, or in this, for surfaces. Well, by Enriquez Zariski, you get cohérents, this vanishing. Well, this works even if M is of larger dimensional, but you will get only this H1 assertion or this HD-1 assertion in cohérents. As far as I know, there is no algebraic proof of the whole cohérent vanishing in all degrees. But so I read that at some point Grauert was at some purely algebraic proof, and it quite possibly the same proof as this one, because this kind of consideration of total space of vector bundles is an old trick of Grauert that he used in this paper with Andreotti and Grauert about pseudo-concavity and in many other places. But anyway, I suppose it's a good place to stop.